Hello, Professor. This is Ryan Macwan. Let me run my code for you. Run main. Let's do easy breadth first search. You can see this is the result. I used BFS, length is 6, cost 17, space is 36, which is the maximum size of the queue or deck, which I used. Time took about 10 milliseconds. Let's do a medium depth first search. This is going to take a few seconds. Took about 4 seconds. The length was 730. Cost was that of 3625, and the space was about 60,000 nodes, which is the maximum size of the deck. And here is the list of all the moves you have to take, which in this instance is going to be about 730 nodes if you do DFS. Let me show you A star 2. A star 2 took about 7.6 seconds. Length is 31. 128 is the cost. Took about 25,000 nodes to find the solution. Again, here's the moves you'd have to make. Here's my main loop. This is the BFS loop right here. I use a deck, an array deck. The nodes are then added. If the node has already been seen, we grab the children for it. If it's not been seen, then we find out what the moves are for that node that are possible. So we go to the successor function, which is the check moves. The check moves function checks each space in the square and checks whether you can make a right move, a left move, a move up, or a move down. Once that move is possible, we then see if we've seen this move before. If that move has not been seen before, we then add that node to the children of the parent node, and then we add it to the scene list. And the scene list is a hash set which contains integer representation, an integer list, which is a representation of the square. We then return all the children of the given node. This will then loop until the goal is checked, until the goal is met. If the goal is not checked, then it will catch an error. No such element exception. We'll then get the solution and print the path. For BFS, I add the children to the end of the deck, and then we pop them off of the beginning of the deck. Queue remove. DFS is exactly the same, other than the fact that we add the children nodes to the beginning of the queue or the deck. This last one, other search, is for the uniform cost, best case, or best cost, and A star 1 and A star 2. I use priority queues, which allows the nodes to be bubbled up to the top of the queue automatically based on a comparator, which I've created. For the uniform cost, I made a node cost comparator, which bubbles up nodes based on the total cost, which is the sum of moves all the way to that node. For best case, or best cost, I believe it is, I use the incorrect tile comparator, which bubbles up nodes based on the number of incorrect tiles for each of those two nodes, for each node. Then A star 1 comparator and A star 2, which is the total cost plus number of incorrect tiles. A star 2 is going to be the total cost plus the Manhattan distance. And so for my other search, I made the priority queues. And so whenever you add the children, it just gets added onto the end of the priority queue, which is in this line of code. And then when we remove nodes, it's going to be from the beginning of the queue, since the priority queue will bubble up the least the node with the least cost on it. And that is all I have for the video. Thank you.